Today, we are beginning a journey from basic electrical theory to real-world engineering. Academic training often focuses on memorizing abstract equations and textbook diagrams without showing how those concepts interact with physical hardware. We will use the Practical Project Blueprint, a 5-step framework designed to take a textbook concept and translate it into a functional design. This framework provides a standard process for passing technical interviews and executing safe physical builds in the field. Step 1 is defining the core theory. Start by selecting a singular objective, such as the basic process of starting an industrial motor. Strip away the jargon. Define what the motor must do in one functional sentence, such as activate the motor when the start button is pressed. Step 2 is selecting the equipment. This is where we move from schematic symbols to identifying the actual physical hardware required for the task. This comparison shows the difference between theory and practice. A generic schematic line becomes a specific physical component, like 2.5 square millimeter copper wire. Textbooks assume ideal conditions, but factors like ambient heat and voltage drop dictate if a component functions over time. Selecting equipment based on these real-world tolerances helps prevent component failure and keeps the system operating within its physical limits. Once you have your parts, move to Step 3, Circuit Design. This is where you map the physical connections between your hardware. This schematic shows a power source running through a relay to reach a motor. A functional design requires an unbroken current path from source to load. Manually trace this path to verify the logical flow before starting physical work. A visual map requires mathematical verification, leading to Step 4, Calculations. Calculate the actual load based on selected components. Take the power rating and divide it by the voltage. Since systems face unpredictable variables like inrush current, adding a safety margin provides a mathematical buffer. Using clear formulas ensures the math remains a practical tool for design rather than a source of confusion. Applying a specific safety margin ensures that the components operate within their rated capacity, even during peak demand. The final phase is Step 5, Problem Solving and Prep. This focuses on what happens after the system is installed. Review your circuit and formulate 2 specific what-if-it-fails scenarios. For example, if the circuit breaker trips immediately when the motor starts, what is the first component you check to identify a short? Proactively identifying failure points is a core requirement of fieldwork, allowing you to troubleshoot issues before they result in a total system shutdown. Review your 5-part blueprint. You've established a goal, selected hardware, mapped the circuit, calculated the loads, and planned for troubleshooting. You have moved from a theoretical concept to a calculated plan that accounts for physical hardware and circuit logic. Applying these principles to real-world projects allows you to verify your knowledge through direct physical results. Tell me which textbook concept you are working to design in the comments, and let's continue the journey of becoming a better engineer together.